a new way to create black holes, and it could unlock quantum gravity. The first step toward quantum gravity, the holy grail of physics, may be hiding in a quantum recipe to cook up black holes. Black holes are relevant to this because they first theoretically emerged from the solutions to the Einstein field equations that underpin general relativity. That's the suggestion of new research that adds quantum corrections to Einstein's 1916 theory of gravity, known as general relativity. This quantum correction leads to a new recipe for making black holes and a hint at the path to quantum gravity and a unification of the two dominant theories of physics. You may like an illustration of a hazy blue background with two black circles with lots of orange dots around it. New theory could finally make quantum gravity a reality and prove Einstein wrong. There is a wave of pinkish gas trailing behind each of them, a purple-hued image showing two black circles, circling around one another in the center. What can ripples in space-time reveal about black holes? Quite a bit, it turns out, an artist, and hash 039. Illustration of two black holes spiraling together, creating gravitational waves in the process. Black hole dance illuminates hidden math of the universe. Click here for more space.com videos. While general relativity is the best model we have of gravity in the universe on large scales, and quantum physics is the best description of the subatomic, these theories won't unify. The violent and turbulent supermassive black hole of M87, that's because, despite the fact that both have been around for about a century, we usually describe them using the theory of general relativity, where black holes appear as solutions to Einstein's equations. Research-led author and University of Sussex theoretical physicist Xavier Calmette told Space.com. However, there is a singularity at the center of black holes, where the laws of physics as we know them break down and have been refined and confirmed a multitude of times. There's still no theory of quantum gravity. This is also despite the fact that quantum physics can account for the remaining three of the universe's four fundamental forces: the electromagnetic force, the strong nuclear force, and the weak nuclear force. However, quantum physics and general relativity do have something in common. Neither can explain what happens at the heart of black holes. Two glowing orange rings of similar sizes, the one on the left is distorted. Physicists don't like infinities because they are intrinsically non-physical. And when they occur, it represents the failure of the equations that underpin the laws of the universe. The relatively quiet black hole at the heart of the Milky Way string theory, which replaces particles with subatomic vibrating strings, has emerged as the leading theory linking general relativity and quantum physics, and thus giving rise to quantum gravity. Additionally, it relies on the universe possessing at least 11 dimensions. All they needed to know was that any proposed theory must fit in with Einstein's theory of gravity on large scales. Calmette said, "This information is sufficient when using modern methods in quantum field theory to perform calculations in quantum gravity without needing the full knowledge of the underlying theory of quantum gravity. And currently, there is no evidence of dimensions beyond the 3 dimensions of space and the 1 dimension of time. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape." Get the Space.com newsletter, breaking space news, the latest updates on rocket launches, skywatching events, and more. One drawback of using our approach to quantum gravity is that we cannot build our solutions close to the singularity. As this is where the full knowledge of quantum gravity is required, your email address, it must be replaced by a quantum theory of gravity, which unifies Einstein's equations with quantum physics, Calmette said. This is the holy grail of theoretical physics. Contact me with news and offers from other future brands. Receive email from us on behalf of our trusted partners or sponsors. By submitting your information, you agree to the terms and conditions and privacy policy and are age 16 or over. That's because we can only observe black holes from great distances, Calmette said. These new solutions are not just tweaks to the old one, they entirely new black holes that exist in a quantum gravity world. As the two theories coincide on large distances, it will be difficult to propose tests able to differentiate between the two types of solutions. At those singularities, the density of black holes goes to infinity. Thus, that singularity at the heart of black holes suggests to physicists that the theory of general relativity is incomplete, and what could be missing is quantum gravity. We believe that general relativity only works on large or macroscopic scales. but that on very short distances, or microscopic scales, is the holy grail at the heart of black holes. Physicists have been looking for a recipe of quantum gravity and a unification theory for some time now. However, currently, there is no way to experimentally verify this theory. Surprisingly, for Calmet and collaborators, the lack of a unified theory wasn't a hindrance. While we do not yet have a theory of quantum gravity, we know that whatever this theory might be, string theory, or something completely different, it must match general relativity on macroscopic scales using these techniques. We can calculate corrections to Einstein's equations that must apply to any theory of quantum gravity. Albert Einstein. Einstein, the father of general relativity, which gave rise to black holes, but Q and I'd be unified with quantum physics. What Calmet and colleagues found is that in addition to black holes emerging from the solutions to the equations of general relativity, there must also be quantum solutions to black holes. We can construct these solutions analytically close to the event horizon, the outer light-trapping surface of the black hole, and far away from the black hole, he explained. That means that the team can't tell if their quantum recipe for black holes leads to the same morphology for black holes as that which emerges from general relativity. It is nevertheless important to have shown that there are new black hole solutions in quantum gravity that do not exist in general relativity. As such, the University of Sussex researcher thinks that this work is still a step toward understanding how quantum mechanics and gravity work together. Related stories? The supermassive black hole is eating way too quickly and burping at near-light speeds. Tiny primordial black holes created in the Big Bang may have rapidly grown to supermassive sizes. Astronomers simulate a star's final moments as it is swallowed by a black hole, breaks like an egg, unfortunately. Even Calmet doesn't yet know how the two potential recipes of black holes, general relativity versus quantum gravity, could be distinguished. The astrophysical black holes we are observing could very well be described by our new solutions rather than those of general relativity, Calmet concluded. Thus, at least for now, the secrets of quantum gravity may be fiercely guarded by black holes.